All right, second to last section. We have integration, numerical integration, excuse me. This consists of two rules, trapezoid and Simpson's rule. Um, if you want to go into the theory of this, go check out the book. They break down the integral, like where it comes from. I have a feeling most people don't care. So we're going to focus on the how instead of the why. If you really want to talk why, let me know. We can make that work. So trapezoidal rule, I just call it the trapezoid rule. If f is a continuous function on a, b, where a and b are your limits of integration, we can estimate the integral or the area under the curve by taking your limits of integration, b minus a, over 2n, where n equals the number of regions. So we break our function, our area up into different regions. The higher your n, the better your estimate. And then once you find that, you take your f of x, so your original function here, times your first limit of integration, plus 2 times f of x times the next one, keep multiplying by 2, times your b value. So this will be your a, and this will be your b, and you find your n, find our delta x equals b minus a over n. So our x0 equals a, x1 equals a plus delta x, x2 equals a plus 2 delta x, etc. You keep going until you get to your final step, which should be your b value. So we could solve this problem pretty easy. It's integral of e to the x, which is just e to the x, makes it nice. But let's use the trapezoid rule on this. So our n is 4. So I plugged that in already, and this is my delta x. So then I take my a value, so this was my a. My x1 is a plus 1/4, a plus 2/4, 3/4, etc. So we're going to say the estimate of our integral is b minus a, 1 minus 0 over 2. We said our n was 4, times. Okay. Our f of x is e to the x. So I'm going to say e to the 0 plus 2 e to the 1/4 plus 2e to the 2/4, which I know is just 1/2, plus 2e to the 3/4. And my last thing, we don't multiply by 2. We just have e to whatever, and that's just to the first power. Okay, I am going to throw these. Actually, I'm just going to throw this whole bit in my calculator. E to the 0 is 1, so I have e to the 0, whoops, 0 plus 2e to the half, no, to the 4th, plus 2e to the half, plus 2e to the 3/4, plus e to the 1st. Okay. I threw this in my calculator, nothing more than that, and I get out roughly 13.8178. Good enough for my purposes here. Divide that by 8. I feel like something went wrong, but maybe not. All right, let me double check this. E to the x x 0, 1, oops, 1. Okay, no, it's good. I needed to double check, so we're good. We get something actual. So I threw just this in my calculator because my calculator will solve these for me. And it told me it was approximately 1.17, excuse me, 71828. So that's what it gave me for limit for the actual integration. We're pretty close. We're 0.01 away, roughly. So it's a pretty good estimate. These are tedious problems. I'm not going to lie. I never liked these just because it was so much hand calculation. Do as much as you can on a calculator. I would write the formula out, find all your x sub whatevers, plug it in, and go from there. It just takes a long time. All right. Simpson's rule is very similar, except this time we take x to the fourth, 4 times our function, 2 times our function, 4 times our function, 2 times our function to the end. And then our endpoints are 0 times that. Okay, same deal, same setup. x0 equals 0. x1 is a fourth. x2 was a half. x3 was 3/4. x4 was 1. And plug it in. b minus a, 1 minus 0 over 3 times 4. Alrighty, so we're using e to the 0 plus 4 e to the 1/4 plus 2e to the half plus 4e to the 3/4 plus e to the 1. I'm again going to throw this in my calculator, and we should get a similar answer to what we did before. Oh, whoops. Okay, divided by 12. Oh, good, we did. For the record, I didn't clear my calculator, so I didn't throw that exact number in. I just wrote down whatever was in my calculator and left it there and divided by 12. Makes the math easier, like the calculations easier. So this number was pretty similar to what we found before. This one is a slightly better calculation. Yeah. But neither of them are terrible. Honestly, I view these opinions, they were great when we didn't all have access to systems to solve these for us. The estimates anymore, we don't need them because we have lovely computer systems to solve these things for us. So I kind of see these going by the wayside at some point. But it is a nice estimate and helps us like get an idea of what we're looking at. The last bit, I am just going to present this, our error analysis. So the trapezoid error, make sure you take the absolute value of that. You can see this one. I'll read it to you. The big thing here, the maximum of the second derivative absolute value. So look at your function. You need to look at your biggest point here and technically your lowest point down there. There we go. And see which one's bigger. So if this was A, this is B, if B is greater than A, absolute value wise, that's going to be your maximum. So be careful with the absolute values. And that is atrocious handwriting even for me. Remember, this notation of x parenthesis 4 means take the fourth derivative. So, yeah. I don't think homework's going to have you do too many of the error analysis, but if they do, now you have that information. All right, one more video, which is coming up shortly.